Okay, we have talked about the different aspects of the atmosphere. Uh, Now we're going to explore where the energy that drives the atmosphere comes from. And that energy all comes from the sun. So without the sun, we wouldn't have all the atmospheric motions, the things we're used to. So, how does this energy flow into? And oh, yeah, we got to maintain a balance. So, how does it flow out to keep our planet habitable? Uh, so we got to learn a little bit about electromagnetic radiation. Believe it or not, you all deal with it every day. You look at it when you look at light, you can see people. That's electromagnetic radiation. Uh, Bluetooth is electromagnetic radiation. So they're all ways, even your Wi-Fi in the house or anywhere at college or whatever that you might be connected to is an electromagnetic radiation carrying signals. So each one of these, and there is a whole range of wavelengths of them. But most of the ultraviolet wavelength is where our sun comes from. So let's talk a little bit about what a wavelength is. A wavelength, if you were out in the ocean and had a wave come at you, and you can see the high part of the wave coming and it reaches you, then it goes down into a trough a little bit, and then the next wave comes to hit you. That's the wavelength, the length between those two peaks, or the length between the two troughs. How frequently they hit you is the wave frequency. In other words, if I'm out in the ocean and if I'm getting rocked back and forth all the time, I have a pretty high frequency of waves. If there's one and then, hey, I can float a little while and then another one comes, it's very low frequency of waves. Interestingly, the speed of electromagnetic radiation is the speed of light. So all electromagnetic radiation moves at that speed. And we make an assumption about black bodies. Black bodies absorb all the radiation it receives and re-emits it. And it makes everything a lot simpler if we assume everything is a black body. So we treat the sun and the earth literally as black bodies. So with that in mind, we know that the temperature divides into a constant of proportionality. So in other words, the bigger the temperature is, the smaller the wavelength. Well, guess what? The sun is a whole lot hotter than the earth. So the wavelengths are going to be a lot hotter and a lot smaller. That's why they're called ultraviolet, because they're way down in the shades, whereas infrared is what we have from the earth. Now, interestingly, temperature of a black body to the fourth power is how much energy it's putting out. Well, again, the sun is a whole lot stronger than the earth, and you put that temperature to the fourth power, and it is ridiculously the difference in the amount of radiation that comes out from the sun compared to that from the earth. So the sun is a tremendous emitter of electromagnetic radiation. Also, depending on how far you are from the sun is how fast you lose your radiation. If we assume the Earth is 1 astronomical unit from the sun, then we take another distance that is twice as far from the Earth. We would wind up squaring it, so it would only receive 1/4 the amount of energy that the Earth does. So it's not equal. In other words, you don't go out 2 and you're half, you go out 2 and you're fourth. So that's why the faster you go out in our solar system, the much weaker the radiation becomes. Okay, now the sun doesn't strike the Earth directly straight on, except at the equator and between the Tropic of Cancer and the Tropic of Capricorn. So that is the only place the sun is going to look like it's directly overhead. That means where we live, the sun's coming in at an angle. Well, if you did it with a flashlight, you'll see that the area covered by energy coming straight down from the flashlight is much smaller than that that's spread over at an angle. So the same amount of energy reaches the Earth from the sun at every point, but it is spread over a much greater area up here in the north or the south compared to the equator. So there's a much more intense amount of radiation reaching the equator than there are up at our latitudes. We spread it out. So with that, and as our Earth rotates around the sun, the axis shifts, and you can see here that, the north pole tilts away from the sun in the winter and doesn't have any sunlight. It gets no radiation. And here you can see that. It's interesting. This tilt doesn't change. The Earth is always tilted this way, except if rotating around the sun, so that December 21st, Northern Hemisphere, we're tilted away from the sun. June 21st, we're tilted towards the sun. That means that 22.5 degree angle that the Earth is tilted, we have that much. The sun is striking directly 22.5 degrees north on June 21st. On December 21st, it's striking 22.5 degrees south. So literally, right now, the sun is heading south of the equator, right? Once we get to the equinox here, the sun will be moving south of the equator and remain there until springtime, when it comes back. Now, all this energy that's coming in, all this radiation, what happens to it? Well, some of it is absorbed by the Earth. The atmosphere absorbs some, the Earth itself absorbs some, and some is scattered. In other words, say it reflects off of ice or snow, reflecting back into space. It's a cloud. Some of the sun's energy is lost from that cloud, scattered all over the place. And the Earth sends so much back as infrared radiation. Remember, the Earth is treated like a black body. But all of that has got to equal 100% of the radiation that arrives. And it does, because the temperature of the Earth doesn't change dramatically over time. So we know that this is about right. So the scattering, they move in all directions. When the sunlight hits the top of the clouds, it moves in all different directions. So some of it goes back into space, some of it goes other ways. Reflection off the clouds, or albedo as it's called, is another method. Now, we talked about that earlier with seeing snow having a very high albedo. Absorption. Some of the energy is absorbed by ozone, which breaks up that ultraviolet and allows the stratosphere to get warmer because of that. And here you can see the light reflecting off the snow, how much brighter it is than the oceans or the land even. And you can actually see the bodies of water in the Great Lakes and how much, if they're not going to have ice on them, which they do right here a little bit on Lake Erie, reflects it a whole lot more. So here are the percentages. Reflected by the Earth system is 30%. 23% is absorbed by the atmosphere, and another 47% is absorbed on the Earth's surface, the heat, the soil, the ground. Total of 100%. Now, if we didn't have greenhouse gases, the average air temperature would be significantly, and I mean to the point where we would not be able to live here, significantly colder. The greenhouse gases are what keeps us alive. However, too much of a good thing is never always good. They are what absorbs the infrared radiation from the Earth. They don't absorb ultraviolet radiation coming in from the sun. They allow it to go through, to reach the Earth. But then the Earth sends it at a different wavelength, gets absorbed by a greenhouse gas. Greenhouse gases are, for example, methane, carbon dioxide, water vapor. The biggest contributor is water vapor. So the more clouds, the more greenhouse gas. And what they do is they absorb that radiation, and then they retransmit that radiation both upwards and downwards and sideways, so that some of that radiation comes back down to the ground and keeps us warmer. Interestingly, if you want to prove how important water vapor is, think about going into a desert. At night, temperature really drops very quickly. So dry. There's very little water vapor. Now, if I go to an area that gets a tremendous amount of rain, like a rainforest, the temperature does not drop at night that fast. As a matter of fact, all that water vapor absorbs the infrared radiation coming from the sun, transmits it back down to the earth, so that this earth cannot cool as fast as where it's dry. So that's how you prove that water vapor is the most important greenhouse gas. And the calendar effect just calculates the measurement of how much CO2 is increasing. It is going up faster and faster continually. And we know CO2 is a greenhouse gas, so we know it's going to absorb radiation from the earth and retransmit it back down. But with that in mind, I wanted to just show you one quick, and here you can see if you're just a crazy mixed up mess of how incoming solar radiation gets absorbed by water vapor, by ozone, by clouds, absorbed by the ground, long wave infrared radiation gets retransmitted here and here, emissions from water vapor back and carbon dioxide. So it's a very confused picture. Yes, we know what it does. We have these approximations. And when we're trying to model it to get a high temperature for the day or a low temperature, this all goes into that. And if you really want to look at, interestingly, all this radiation that's going back out into space from infrared, that is what's so neat about our satellite system that we have for weather. We have a geocolor. What that is all radiation that's going back out into space. We can see it. We can do air masses, which are different other radiations or sandwich. Here, for example, is band 1, which is more of a blue visible or red visible. Here we can look at the vegetable radiation, a cirrus, which is a high clouds. You can get water vapors. All of this, different bandwidth, indicates different things in the atmosphere. So we can actually pick out, we talked about water vapor, carbon dioxide emits radiation at a different wavelength. So we can look at that wavelength and pick it up right here and get an idea of what's going on. So hope you get a little bit out of this and understand it. Let me know if you have any questions.